Okay, works. So yeah, so thank Holly for the introduction. So this work is a collaboration with my student Zhiqian from as well as people from Meta. And since Zhiqian couldn't come for this conference, unfortunately, I will be presenting his work. And okay, so this work is mainly about appearance acquisition, which is a fairly classic problem in computer graphics. Here we focus on appearance acquisition, meaning that we assume geometry and everything is known. But even then, the problem is far from trivial because in the reality, we have lots and lots of materials such as metal, wood, fabric, etc. They all reflect or refract light differently. And the objective for appearance acquisition is, of course, to acquire all those BRDF, or even spatially varying BRDF parameters from the real world or from physical samples. Of course, to acquire appearance, we need to first describe them. So a popular way to describe appearance is, of course, to parameterize them, as opposed to just brute force tabulated representations. So there are many ways to parameterize BRDFs. So here we are showing an example using, say, Disney's principled BSDF with a bunch of parameters. Of course, in this work, we do not assume for any specific parameterization, but we do in general assume that the appearance or the reflectance of an object is parameterized with a relatively small number of parameters, which can vary across different surface locations, but angularly speaking, we assume there's some underlying parameterization. Okay. So you may wonder, okay, if we assume that the geometry or the shape of everything is known, the line is known, how can this be a hard problem? Because we can, with all the differentiable renderers and everything in hand, can we just run gradient descent and get everything and be done with it? Unfortunately, the answer is not really. A main issue here, which is also what we try to quantify, is ambiguity. So the problem is that when we have a number of acquired images, like photographs of some real world object, to figure out the material parameters that would be able to reproduce all the input, all the observations, there is normally, or even most of the time, many potential solutions. So in here, we are showing kind of an extreme example where we take a very small number of input of like a greeting card. And you can see on the right, there are very, very different material parameters. So here in the hopefully you can see my mouse. Let's see if we can see it. Yes. So in the first column, we're showing kind of diffuse albedo, normal map, roughness, and like specular albedo. You can see very different combinations of material parameters can all lead to essentially the same appearance or the same rendering. So if you render any of these combinations, you get the same image. So then the question is, of course, which is the correct one? And this, in fact, is a fairly fundamental problem that has existed for forever. So to address this, of course, there are a lot of prior works that try to address this. The first type of method, of course, is the brute force way. The more observations we make, hopefully, the less ambiguities we'll have. So because of this, a large family of previous appearance acquisition methods focus on, for example, how to efficiently get dense observations. And of course, there's another type of prior methods that focuses on introducing powerful priors without the need of dense observations. So here I'm just showing a very sparse sampling of prior methods for both categories. If you are interested in each of them, you should be able to find tons of works. However, what we are trying to achieve in this paper is to answer a problem that still remains, which is how much ambiguity is still there, regardless if you are making dense observations and using potentially powerful priors. So to be more specific, our contributions involve a statistical formulation for quantifying uncertainty. To be more specific, we try to do that, as I'll discuss later in a few slides. We try to quantify uncertainty in both parameter and image spaces. And we also introduce a method to graphics to efficiently sample posterior distributions. And based on this formulation, we also introduce a proof of concept method to guide capture processes to reduce uncertainty. So here is a preview of our result using real data in this case. So let me explain what's being shown here. So here we are showing a kind of material reconstruction of a real horse object under collocated configuration. Collocated configuration means we take a picture with a cell phone where the light source is essentially a point that's collocated with the camera. So what we are showing here, our result is actually just the last column, which is kind of a heat map that tells how uncertain or how much ambiguity it is in this rendered image. So here, the rendered image uses a novel setting, meaning that it uses an angle that's not captured, and which is the ground truth here. And the middle columns, the four middle columns, are re-renderings of four reconstructions using traditional methods like gradient descent methods, using different initializations, etc. So the four columns are re-renderings of traditional reconstructions. And on the bottom, what we want to show here is the interesting thing is on the bottom, we show the errors of these re-renderings. So these are the 1, 2, 3, 4. These are error images. The fifth column, again, is our ambiguity prediction without actually looking at any of these re-renderings. So what's interesting here is that you can see the error in re-renderings correlate strongly with the ambiguity that our method kind of predicts, as I will explain how they are defined. So again, as you can see in this paper, we are more of like asking questions than answering them, because we're trying to tell you, right, that, oh, in this region, whatever reconstruction or all the observations that we are available can't tell, right, whether or not uncertain about the value of this pixel. So this is a paper about asking questions than answering them in terms of how to reduce ambiguities. Yes, we have some proof of concept things, but it's still proof of concept. Okay, so hopefully now you get some idea of what our method does. So now let me introduce how it works. So the background really is nothing new, especially in statistics. It's basically a Bayesian framework, a Bayesian interpretation. So under this interpretation, the knowledge is quantified as a so-called posterior probability, meaning that given some observations y, and in the appearance capture case, y are essentially all the photos you take. And we want to model the posterior distribution of material parameters x. X here would be your BRDF parameters, right? So given all the photos, you can imagine the possible material parameters will form some sort of a distribution, right? That's the posterior distribution. And the posterior is, of course, also dependent on a prior knowledge of the parameters. So the prior can be as trivial as a uniform distribution or as complex as some data-driven learned distribution. And of course, knowledge is updated with the observations y, meaning that if we take more photos, we have a more refined posterior that's hopefully less ambiguous. Okay, so to be more precise about how it works, the posterior distribution here is normally proportional to the prior multiplied with a so-called likelihood function. The likelihood function, you can think of it as some sort of a rendering loss, which given, which basically measures if you have this material, a specific material parameter, will a rendering using that parameter agree with your measurements? That's kind of modeled by the likelihood function. So with all this formulated, you can think of conventional inverse rendering as making a point estimate, meaning that we are trying to seek for, sorry, this should be x. We are trying to seek for, okay, xy is flipped here, but the ordering is still fine. We are trying to find material parameters that maximizes this posterior distribution. Okay, or if we visualize this, it's basically the in 1D case. So here is the posterior distribution. Traditional inverse rendering essentially amounts to find a single point on this distribution. That's the most likely. This works adequately in many cases. However, it has a number of problems, such as it's really not modeling the ambiguity. And also, of course, it's also fairly prone to local minima. So all this process, if you do a gradient descent or ascent, depending on how you formulate the optimization, you start with some initialization, and then you try to just hope for the best that a gradient process can get you where you want. So what we want to do in the first half of our method is really to kind of quantify, given all the observations we have, as well as the prior, we consider the prior is also given. Can we somehow quantitatively describe how much ambiguity is still left? So we do this in two spaces. The first one is kind of simpler. We do so in the parameter space. So the question really is, yes, we have obtained point estimates and so on, but how much ambiguity is there? So intuitively, if we look at the posterior distribution, so here again, we are using a 1D visualization. If the posterior distribution is very concentrated, meaning that it can be bimodal, but one or a few point estimates are kind of predominantly likely, that means we don't have a lot of ambiguity. However, if we have a wide distribution, meaning that many combinations of material parameters could all be plausible, that actually means high ambiguity or high uncertainty. So to do that, we simply look at the posterior distribution, and then we look at the standard deviation of it. So here we took a fairly simple approach where we take so-called basically the component-wise standard deviation, because remember here the parameter space is normally high dimensional. We have albedo, roughness, normal mapping, etc., which can also be spatially varying. So we basically take the posterior distribution and then we compute component-wise standard deviation on it. This basically gives us a uncertainty vector that takes the same shape as the parameter vector, which is why we call it the parameter space ambiguity. Imagine if you are doing like a SVBRDF reconstruction, then what we will get here is an uncertainty map for albedo, for roughness, etc., as I will show later. Okay. And beyond that, we also introduce this notion of image space ambiguity. This is because acquired appearance models are usually used to produce renderings under novel conditions, like with novel lighting, novel viewing angles. So we want to we introduce this ambiguity also in the image space. In this case, we directly quantify ambiguity by using the rendering function. So here, x is the random material parameters subject to the posterior distributions. However, rather than looking at just the standard deviation of x itself, we look at standard deviation of a rendered image using material parameters that are random. So the randomness of x causes the rendered image r of x to also be random. Okay, so r itself is a deterministic function, but because x is random, it causes the rendered image to also be random. And in fact, this image space ambiguity is what I just previewed before talking about our method. So that's the ambiguity that has been demonstrated to closely correlate to rendering error if you take a point estimate. Okay, so as you can see, in both cases, we need to estimate standard deviation. So the question is how we do it. To do this, we need to draw samples from the posterior distribution. So this is a quite standard task of sampling, for drawing samples from posterior distributions. It's a fairly well-studied problem in computational statistics and machine learning. So in practice, there are two classes of methods that are commonly used. The first one, I'll briefly go over each of them. The first one, which is also probably more familiar in the rendering community, is Markov chain Monte Carlo, which has also been used in rendering. The idea is really to construct a Markov chain samples using methods like metropolis hasting. And once you generate enough samples, the equilibrium distribution would match the target function, such as the posterior function. However, this method, hopefully I can show the animation here, is not super robust in many cases. And as you can see here, when the target distribution is like a ring-shaped, metropolis hasting can get stuck in a certain small area, even when you use fancy methods like Langevin Monte Carlo or Hamiltonian Monte Carlo. So because of this, there's another family of methods which has gained popularity recently in computational statistics, which is called particle optimization sampling. So the idea here is really to use a set of particles to represent the samples and then directly optimizing their positions so that in the end, the distribution of those particles approximates the target distribution. And so I omit the technical details and also just show a simple example using the same target function. So as you can see here, at the beginning, we have a bunch of particles that are randomly distributed. So what this process does is to iteratively optimize the distribution, the positions of all the particles by simulating certain forces, so that in the end, when convergence is reached, the particles are distributed by following the target distribution. So in practice, we utilize this a stochastic version of this method. So it works by starting from some initial distribution and then just iteratively update the particle positions. And people in computational statistics have evaluated this so-called SPOS method by quite a bit, and we can see that variance-wise and error-wise, they are pretty performant compared with more traditional methods. And also, we have observed in our work that this method also scales fairly well to high-dimensional situations without the need of too many particles. Okay, so we basically use this to compute. In our case, we utilize this method to compute all the standard deviations that we need to define the uncertainties. Okay, so with everything, we try to answer an important question, unfortunately only in a proof of concept way, that is it possible to make observations in a clever way so that uncertainty is minimized. So to be more specific, we answer the following problem. Consider we have a set of predetermined configurations, such as a dense set of lighting and viewing combinations. And what we try to do here is to basically select a sequence of configurations from the predetermined set so that hopefully ambiguity is minimized. So to do this, we have a proof of concept greedy solution. Assuming we already have a sequence of observations, configurations, and corresponding observations made under those configurations, what we do is to select the next configuration from the set that maximizes something called mutual information. The key here is really consider R of theta. Theta here is a configuration, like a viewing and lighting thing. It's still random because the material parameters is still subject to the posterior distributions here. So as mentioned here, since I don't have a lot of time left, I will omit the details. So if you are interested in it, please see our paper. The reason why it's still proof of concept is because the selection process that maximizes mutual information is still extremely expensive. So at the current state, you might as well just take all the configurations, which could be faster. Okay, now let me show some of the results. So here we show a result that demonstrates parameter space uncertainty. So here you can see we are showing two example input images here. So we are taking a number of input images under collocated lighting and then try to predict SVBRDFs involving diffuse albedo, etc., and roughness, etc. So something that we can see here is that let's see. Okay, here. So in the first column, we're showing estimated uncertainties with just 3 input of the images. In the middle column, we show estimated uncertainties with 10 input images and as well as 100 of them. So here we should focus on the bottom row, which is the uncertainty. The middle rows are errors of point estimates. As we can see here, the uncertainty decreases when we use more input images, as expected. Okay, and also interestingly we can see that with fewer input images, the uncertainties are not uniform. There are certain regions that are more uncertain than others, potentially depending on whether you have seen a highlight or not. If you have never seen a highlight in a certain area, you are more uncertain about the roughness, as opposed to when you do see a highlight. That's why if you look at the first 2 columns, there are some blobs that are lower in uncertainty. These are where the highlights have been observed. Okay, so here is some more image space uncertainty, similar to what I previewed. Again, these uncertainties are computed using collocated input. However, the re-rendering can be under any condition. The re-rendering can use, say, environment lighting as well, because we are really just looking at the standard deviation under a fixed setting where the material parameters are random. Right? So the configuration can be very different from the configuration used for capture. So here, again, we are showing similar things. You can see here, on the rightmost column, we are showing the estimated image space uncertainty. That's the standard deviation of rendered images. And we can again see that the point estimates that we obtained using different methods and different initializations correlate strongly with the uncertainty. Something to be aware here is that high uncertainty doesn't always lead to high error, because you can have a point estimate that just get lucky, right, to end at the correct solution. But if we look at different point estimates, you can't always get lucky. Sometimes you're unlucky and predict something that's very off. But on average, you can see that high uncertainty area would normally correspond to high image error under normal settings. Again, the power of our method here really is that all these uncertainty maps are computed without considering any specific point estimate. So here we show another image space uncertainty. So in this case, the reconstruction or the observations are taken under environmental lighting. Again, when we compute uncertainties, they can use totally different configurations. And again, we see the same type of correlation between uncertainties and image rendered errors using novel settings. So finally, we show a guiding result using the proof of concept methods, the greedy one that I just mentioned. As we can see, compared with a baseline that just uniformly samples the viewing direction, our method the guided method can indeed lead to lower uncertainty as well as lower rendering error under novel settings. But again, it's not practical yet because it's super slow. Okay, so our method has a bunch of limitations. The first one is that we really didn't model the limitation of the parametric BRDF model itself, because when the model cannot capture the real photo, there's another source of error, which we didn't model. And also we didn't model the rendering noise because we have some rendering of it. We are assuming that the rendering function is deterministic given the material parameters, which is not the case if you use a Monte Carlo process. And we're also not modeling ambiguities in illumination or shape. So we're focusing on just, say, BRDF parameters. And as I just mentioned, our capture part is still very slow. So we need to make it practical. So to conclude, we have introduced a kind of formal formulation for parameter space and image space uncertainties. To do that, we also showed how SPOS can be used to more efficiently sample posterior distributions. And we showed a potential method to utilize those quantified uncertainties for more efficient acquisition. Okay, thank you.